Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in the last week of this course, and as we planned earlier, in this week we are going to cover different topics so that you get a complete view of the design challenges that we often experience when we design a full-scale building. Now for that, we identified a couple of topics to cover in this week. Their design details we have already covered earlier, but we'll consider some advanced examples to further clarify the doubts or the challenges that you may experience when you design actual structure. So for that, we are going to cover these list of topics as you can see on your screen. So the first we will revisit underground tank. Now recall we had a dedicated week for underground tank, but here we'll take a very specific problem and we'll see how that specific problem actually offers a serious challenge and how we can actually design the underground tank. Then if you recall, when we discussed the design of column, we faced the most critical case where a column experiences biaxial bending. We did not cover that at that time because that was the first time you were introduced to the design of column. So we thought to continue so that you get time to just go through all those theories and examples. Then that time we planned that at the final week we will revisit this example. So we'll consider column with biaxial bending. Then we have a series of topics where we'll consider a full-scale building. Now, if you recall the entire course where we designed the structural components, for example, we started with the roof slab, then we designed the beam, then we considered column, and then finally footing. So these are the different structural components we have in a frame structure. Now, in this course, the final week, we are going to model a complete structure in finite element framework. Now, obviously, we'll not go into the details of finite element theory. That is not possible in this course. However, we will show you how we can use commercially available software and then we can completely model the building. Okay. So for that, we will use STAAD.Pro because STAAD.Pro is very popular in India and it is used in industry to model and design the structure. So first, we'll consider a full-scale building and that we'll model in STAAD.Pro. Then we'll go for load analysis. And for that, we'll again revisit different types of loads, how we can apply them and do a static analysis because in our design, we do a static analysis. And it will be followed by a new concept called modal analysis where a structure vibrates with its natural frequencies and how to find out those natural frequencies for a full length structure and what are the codal provisions we have that we'll go through. So I will briefly introduce you to the concept of natural frequency and free vibration, and then we'll use again STAAD.Pro, the same model of the building, and do the modal analysis to find out the fundamental modes, the mode shapes, and how the structure vibrates in different modes, and what is the meaning of modal participation factors. Of course, again, we'll not go into the details of the theory of vibration. Those who are interested, you can go through the theory, but I will briefly introduce you what are the meaning of natural frequency for a full-scale building, right? Then we will revisit the design. So we'll use STAAD.Pro to design the entire building. And again, we'll follow IS 456 for this design. And we'll see what are the design steps, how we can complete the design and how we can redesign a component. Because if you recall, design is an iterative process. If one section fails, and obviously we need to redesign that again. So that we'll see. Then we'll move over to response spectrum analysis. This is very important for seismic analysis. For that, first I will introduce to the concept of response spectrum and how we can use the design response spectrum given in our code to analyze the structure. Again, we'll not go into the details of theory, but I will broadly introduce you the concept of response spectrum and how we can use the design spectrum for the analysis. Finally, we'll go for time history analysis. That is also very important for seismic analysis and also wind analysis. But here in this course, we'll only consider earthquake load, which is applied as a ground motion. So the supports of the structure will experience that acceleration. We normally record those accelerations during an earthquake. And when you come to a particular site, that particular site has a design response spectrum. So we need to first make a spectrum compatible ground motion before we apply that to the structure. Again, I will not go into the details of how to generate response spectrum compatible earthquake, because that involves some mathematical theories. However, I will show you how you can use the softwares to make a recorded time history spectrum compatible, and then we'll use that spectrum compatible motion for the time history analysis of the structure. So that will be the different topics covered in this week. So we are in week 12 and this is our first lecture. And in this first lecture, we are going to cover the underground tank design. So as you can see on your screen, we have an underground tank. Now earlier also we designed this tank in detail. However, this time we'll consider the surrounding soil to be saturated. So that is the only addition we have, and we'll see the moment we consider saturated soil, how the soil pressure is affected, and we use that for the design of the structure. So we have a tank of dimension 10 meter by 4.5 meter by 4.5 meter, and the unit weight of the soil is given, as you can see on your screen. It is 19,500 Newton per meter cube. We are going to use M30 grade of concrete and Fe415 steel. So let us start the design of this structure and let us see what is the impact of saturated soil. Now when we design an underground tank, particularly for this case where we have tank with saturated soil surrounding, there can be 4 different extremes, as you can see listed on your screen. So the case 1 is when the tank is completely filled. So we have water inside and the surrounding soil is dry. That means water table is below this base, so it is not fully saturated. And then that is the first load condition. Obviously, we'll have soil pressure from outside due to this dry soil, obviously, and then the water pressure due to the water stored inside. So case 2, when the tank is empty, so the water pressure is 0 from inside and the surrounding soil is fully waterlogged. That means now it is saturated. Similarly, we have case 3 where the tank is full, so water is inside while the surrounding soil is waterlogged. That means it is saturated. Obviously, when we have full pressure, water pressure inside and full soil pressure outside, they are counterbalancing each other. That is corresponding to case 3. Case 4 is when the tank is empty while the surrounding soil is dry. So these are the 4 extremes, and out of that, obviously the first 2 cases are most critical. We will use those cases for our design. However, you can also cross-verify the design against this case 3 and case 4. That I leave it as an exercise for you to cross-verify. But let us in this example consider the 2 most critical cases, that is case 1 and case 2. Now, let us first consider case 1 and see how we can design the structure. So for that, we have tank is full and the surrounding soil is dry. So the maximum soil pressure is given using this expression. As you can see here, the point to be noted that theta is equal to 30 degree, right? So the maximum soil pressure in this case, we have 29,250 Newton per meter square, and the maximum water pressure inside is 44,145 Newton per meter square. Now obviously we have for case 1 full water load inside applying a water pressure, and then from outside we have dry soil applying a pressure. So the net pressure is the difference between these two, and that is 14,895 Newton per meter square. Now for the design, if you recall, we need to consider 1 meter of the wall and then for that we need to find out the bending moment over the height of the wall, and as you can see, this is the variation of the bending moment. We discussed this earlier. So we have maximum bending moment producing tension away from the water face is pH square by 33.5, which is here, and that value is 9003.7 Newton meter, while the maximum bending moment producing tension near the water face is here, pH square by 15, and that is 20,108.25 Newton meter. So now we have the two bending moments acting on the wall for this load case 1. Similarly, we can also repeat the same exercise for load case 2, but in this case we have tank is empty, that means there is no water pressure from inside, and the surrounding soil is waterlogged, that means it is fully saturated. Now if that happens, that theta, which earlier was 30 degree, now it is 6 degree, and for that the pressure intensity we can evaluate, and you can see the value, it is 71,141.33. We can ignore that small decimal part. So it is effectively 71,141 Newton per millimeter square. Now if you compare that value with the previous one, you can see here it was 29,250 Newton per meter square. So you can easily sense the increase of pressure due to the saturation of the surrounding soil. Then again, we consider 1 meter of wall, and we find out the maximum bending moment producing tension on the water face. In this case, it is 43,003.3 Newton meter, and then maximum bending moment producing tension away from the water face, which is pH square by 15, and it is 96,040.8 Newton meter. Now for this problem, we are going to use M30 grade of concrete and Fe415 grade of steel. And if you recall, the code for this tank is IS 3370-1 2009. So as per this code, sigma C and sigma T for the grade of concrete and steel we use are 10 Newton per millimeter square and 130 Newton per millimeter square. And the modular ratio is 13. So K, J and R, these are the three constants that we are going to use for the design. If you recall the theory of working stress method, here in case of water tank, we are going to use working stress method for obvious reason. So these constants are K equal to 0.994, J equal to 0.67, R is equal to 3.323. Now, before we design the cross section, let us first prepare a table, because we have considered two different load cases as you can see on your screen, and for each load case we have two different values of bending moment. So if we formulate a table, here you can see we have the values of bending moment, and from this table you can easily see the governing bending moment is here, which is 96,040.8. And we will design the cross section against this. Of course, we will also find out, because the other face will have a bending moment of 43,003. So we will find out the steel, but first let us find out the thickness of the wall. And for that, you can recall this expression. So that is the capacity that we equate with the applied bending moment. And the moment we do that, the only unknown in this expression is this capital D, which is the total thickness. And in this case, we have 537 millimeter. So we can provide a wall thickness of 540 millimeter. So if we assume a effective cover of 40 millimeter, then effective depth small d is 540 minus 40, which is 500 millimeter. Now our next task is to find out the area of steel. So we consider the two extreme cases. So for the tension away from water phase, the design value is 96,040. So for that we find out AS, which is 2205 millimeter square. So if we provide 18 phi bar, the spacing of this bar is 115.2 millimeter. So we can provide 18 phi bar at the rate of 110 millimeter center to center. Obviously, the area of steel provided is 2309 millimeter square as opposed to the required area of 2205 millimeter square. So that is the one load case with tension away from water phase, and the other value of the bending moment for tension on water phase is 40,003.3. So let us find out the steel corresponding to that bending moment, as you can see here, and it is 988 millimeter square. So on this space, let us provide 12 phi bars, and for that the spacing is 114.4 millimeters. So we can provide 12 phi diameter bar at the rate of 110 millimeters center to center. Obviously, on this space we provide an area of 1027 millimeters square as opposed to the required value of 988 millimeters square. So you can see the detailing on either phase. We have provided the steel accordingly, and we also identify the water side and the saturated soil side, right? So that completes the design of the side wall. Now, in addition to the side wall, we also have to design the roof slab and the bottom slab. And before that, we also have to check, because this is a water retaining structure, the cracking stresses. So for that, we need to first find out the neutral axis. And you can recall this expression for neutral axis that we derived at the very beginning for working stress method. And if you put all the values which are known, so we get N, which is the depth of neutral axis, and that is 263.9 millimeter. Now we can find out the tensile stress in concrete, CT. From this expression, again we equate the applied bending moment to this expression, and then we get CT is equal to 1.507 Newton per millimeter square, right? So that is less than the allowable value of 2 Newton per millimeter square, so it is safe. So you repeat the same test for the other side where the bending moment is 43,003.3 Newton meter, and for that again we repeat the same exercise. We find out CT, which is 0.706 Newton per millimeter square. Again it is less than the allowable value. So for the cracking stress, the design is safe. Now, as I said, we have two more structural components. First, the design of roof slab. So for that, we need to first calculate the design of roof slab. So we will provide a 130 millimeter of roof slab. But when we calculate the dead weight, we put some additional dead weight so that the design is safe and it is always conservative. So we provide a slab thickness, roof slab thickness of 130 millimeter. But when we calculate the dead load, we add some additional load which may be surfacing or other to keep this in the safer side. So the dead load that we calculate is 4,500 Newton per meter square, and then the live load is 1,500 Newton per meter square. So the total load is 6,000 Newton per meter square. Now again, for this roof slab, we consider 1 meter wide strip, and for that the applied bending moment is 19,051.2 Newton meter. Recall we used M30 grade of concrete, so R BD square is equal to this value of the bending moment. So the D required, small d required, is 76 millimeter. Now if you consider effective cover of 40 millimeter, so D effective, small d, is 130 minus 40, which is 90. Now we can calculate the area of steel required based on the small d value, and which is 2430 millimeter square. So we can provide 25 bars, and for that the spacing is 129.2 millimeters. So we can provide 25 bar at the rate of 120 millimeters center to center. Now if you recall, for the roof slab we have to provide the distribution steel in the orthogonal direction. So we provide 0.3% of the cross-sectional area as distribution steel, and that AS is 390 millimeter square. So if we provide 10 millimeter diameter bars, the spacing is 200 millimeters center to center. So that completes the first part of the design for the roof slab. Next we move over to the bottom slab. Right. Now for the bottom slab, again we assume the slab thickness is 600 millimeter. So first we calculate the uplift pressure the depth is 4.5 meter plus 600 millimeter. So at the bottom, we have to find out the uplift pressure, and which is 50,031 Newton per millimeter square. Now again, if we consider 1 meter of the slab, then weight of the slab is again 16,380 Newton. This is the base slab, the bottom slab. So now we have to also consider the net weight of the two walls. So that is, you can see 1,21,500 Newton. Now finally, base slab is 0.6 times x times this value of 25 kilonewton per meter cube. So we have this x. Now weight of soil on the projecting portion of the base. So here you can see the base slab is projected on either side. So that is the total weight. As you can see, this is the expression, and then we can calculate the upthrust. So we equate the upthrust with downward forces and get this x is 6.67 meter. So the total width of the slab that we have to provide to balance the downward force with the upthrust is, as you can see, 6.67 meter. So the base width is 6.67 meter. So the base slab, again, we have to design for the two load cases we identified at the very beginning of this exercise. So the case 1 is tank is full and the surrounding soil is dry. Now again, for that we have to find out the weight of the roof slab, weight of the two walls. So then the total weight, as you can see on your screen, 1,37,880 Newton. Now one point to be noted is that the water pressure acting on the base slab and the weight of the base slabs are balanced directly by the ground pressure. Hence, they are not considered in the bending moment calculations. So the upward reactions is, as you can see, it is 20,671.66 Newton per meter. So that is marked here, the schematic diagram. We have base width of 6.67 meter, which is supported by two walls, and we have a pressure coming from the bottom. So the maximum bending moment will be at the center, and that we can evaluate using this expression, and the value is 1,73,728 Newton meter. Now this value of bending moment is going to produce tension on the water side, obviously, because this is the inside of the tank. So if this pressure acts, it will bend inside, and obviously it will be tension. It will have tension in the inner side. Now water pressure together with the lateral soil pressure acting on the vertical walls, that will produce additional bending moment of, this is the magnitude, and the total bending moment is the summation of these two. So we have, that is the total bending moment, and that is the tension near the water face. Okay. Now bending moment at the end we have to calculate because we have these supports. So we have hogging bending moment there. Again, this is the hogging bending moment, and the sagging bending moment, similarly we have to find out is which is 6,865.32. Now the net bending moment is the difference of these two. So we get the bending moment that will produce tension on the water face. Similarly, we repeat the same exercise for case 2 when the tank is empty and the surrounding soil is waterlogged. Now, for this load case, the intensity of the uplift pressure due to wall water in the soil, that is, the soil is saturated. So here again, because of the soil saturations, we have higher value of water pressure. Uplift pressure. And then net upward pressure we can calculate, which is 70,114 Newton per meter square. Again, we consider 1 meter width, and the bending moment at the center in this case is 1,99,340 Newton meter. And again, this will produce tension inside. Now, the bending moment at the center caused by the saturated earth pressure on vertical wall is here. We have already evaluated that earlier. Now, this will produce tension away from the water side. So, the net bending moment at the center we can actually find out, which will produce tension on the water side. Then again, bending moment at the end we have to figure out. This we evaluated earlier. So, for the cantilever section, so we have cantilever moment which is 23,285 Newton meter. So, the total bending moment at the end is the summation of these two. Recall, here is the cantilever portion. So, that is the value of the bending moment, which is tension away from the water side. Now, first we have to calculate the thickness of the base slab, for which we equate the capacity with the maximum applied bending moment. And here you can see, once we do that, we have small d is 189.5 millimeter. So, we can provide slab thickness of 550 millimeter and effective cover of 60 millimeter. So, effective depth is the difference of these two, which is 490 millimeter. Then again, we have to find out the steel required for the bending moments that we have identified. So, area of steel required for this maximum applied bending moment is 2796 millimeter square. So, if we provide 24 diameter bar, then the spacing is 162 millimeter. So, we can provide 24 pi bars at the rate of 160 millimeter center to center. So, the area of steel provided is 2825 millimeter square as opposed to the area required, which is 2796. Now, for the other side, we have the bending moment identified. So, area of steel is 2421 millimeter. Again, we can provide 24 diameter bar, the same diameter bar, but the spacing in this case will increase and it is 187 millimeter. So, we can provide 24 5 bars at the rate of 180 millimeter center to center. And in this case, we provide a steel of 2511 millimeter square as opposed to required steel of 2420. Right. So, here you can see the different load cases as we did earlier. Here also we have the different load cases, and from this we identify the different extreme values of bending moment that the structure is going to experience. Now, we also have to provide distribution steel, that is 0.3% and 0.3% of the cross section, which is, if you recall, depth is 550 millimeter. So, AS for the distribution steel is 1650 millimeter square. So, if we provide 16 diameter bar, we have a spacing of 120 millimeter center to center. Then again, for this structural component, we have to check the cracking stress. Repeat the same exercise. You know this expression already we have used for the walls, and for this case of bottom slab, we have N is equal to 273.7 millimeter. And we can find out the CT using the capacity with the applied bending moment, and for that we will get a CT of 1.82 Newton per millimeter square as opposed to the allowable value of 2 Newton per millimeter square. So, the design for this case of bending moment is safe. Similarly, we repeat the same exercise for the other extreme, and then this will produce tension near the water side, and for that problem again we use the same expression and find out CT. CT is equal to 1.59 Newton per millimeter square. So, in this case again CT is less than 2 Newton per millimeter square. So, the design is safe. Now, once that is done, we have to go for a detailing. As you can see, we have the side walls, and you can see the plan view where we have the detailings for the side walls. So, we provide all the stills that we have estimated accordingly and mention their spacings. Then this is the cross section where we can see the reinforcement for roof slab and the base, right? So, you can see different steels that we have identified along with the distribution steels, and that completes the design. Okay, so we have seen how to design an underground tank for saturated soil case. Go through this design steps. If you have any doubt, do let us know. We'll clear your doubt. Thank you very much.